Resume recording. Right, a very good morning. Session number 3. Last time we introduced optical fibers, and we talked of why. I think I gave an assignment why we use more optical fibers, and one of the main reasons in bandwidth, it offers us more bandwidth. The communication here do very much more clearer, more quality. Kuti ikwanise kuti allow to send more data, which is the case nowadays. You need channels which offer you large bandwidth, and one of those channels, DOM optical fibers, and we use it obviously for that main reason. And other reasons, like I said, security, it offers security. It is less affected EMIs, electromagnetic interferences, and so forth. You need to know some of the reasons why we use this. You need to know some of the reasons why we use my optical fibers, my advantages, my uses, and so forth. Right. Last we talked of another V number, and I introduced V number, and I said it is a number. Let me see. V number. It is a number which can be used to determine if an optical fiber is single mode or multi-mode. We went through what are single mode optical fibers, what are multi-mode optical fibers. Briefly though, because I'm expecting you, when you go through the videos, you do a little bit of research on single mode fiber chi. Why Shirishandisa? What are the advantages of single mode over multi-mode? Multi-mode that I gotta say, what are the disadvantages? But then yeah, dispersion, you need to add some beef on that. Very simple things. This is sort of basics. Open up a Google, you do a little bit of research, you can get some information which might be useful for understanding optical fibers. Right, the V number describes the relationship between the numerical aperture and the radius of the core. Relationship between the numerical aperture and the radius of the core. I don't know. These are inversely proportional, I think. These are inversely proportional. If the radius of the core decreases, the numerical aperture increases. No. What is the relationship between these two? If the radius of the core decreases, the numerical aperture decreases. Is this true? Participate, numerical aperture. Participate V over 2 pi a lambda naught. Right. Definition, numerical aperture. Someone to define numerical aperture. Unmute yourselves. This is a discussion. My videos in those 19. For this one, we are discussing. Unmute everyone. All right. Who is there? Numerical aperture definition. Jani Tanaka. Exam range is in 2 weeks. Mukuro fast track. Anyone to respond? What is the numerical aperture?
It's the ability of the lenses to capture light.
Ability to capture light. And how do you think the radius of the core affects the numerical aperture? have two things here which are not going so well. If we decrease the radius of the core, what happens to the numerical aperture? This is theta 0. This is the cone. I think it is related to the numerical aperture. And here we have the radius of the core. If we decrease the radius of the core, what happens to the numerical aperture? It's right there. What happens?
It increases.
Oh, thank you very much. It's right there. That's where the relationship is. Mathematics, a little bit of mathematics reasoning. You have formula way. If A decreases, the numerical aperture increases. That's the relationship. Right. The V number describes the relationship between the numerical aperture and the radius of the core. In the formula, there you have it. V 2 pi over lambda naught, where lambda naught is the wavelength, fundamental wavelength. This is the fundamental wavelength of light. Wavelength of light. Which light? The light you are using to send information. We said optical fibers, it's a medium. What does it use to send the light through? What do we use for transmission? We use light, right? The light, it has a wavelength. It's an electromagnetic wave, therefore it has a wavelength. This is the wavelength attribution to number. A is the radius of the core, and we have the numerical aperture. The V number can be used to determine, to differentiate single mode and a multi-mode optical fiber. If that number is less than 2.408, this means we have a single mode optical fiber. Typical questions. I think I mentioned this in the last videos. Typical questions. You are given N1 and N2. You are asked to find the numerical aperture. You are given A, you are given the wavelength. Find the V number. Find the V number. Then determine if single mode or multi-mode. And you use knowledge, yes, you know how to calculate the numerical aperture, it's a formula. How to calculate the V number, it's a formula. Determination, single mode, multi-mode, it all depends on this number. If the value of V you get is less than this, then it's a single mode optical fiber. Very simple things. These are the typical questions you'll be having in your exams. Right, we are done with the V number. A reminder, this is a sort of a complementary session. Most of the information, Irimoma videos, 19 and Rafin and that, this is sort of complementary in the resuming, giving a summary of the important things that you need to know. And if any questions, but by the looks of it, one question. You have 4 weeks, 3 weeks to be prepared for the exam. And I think what was that 1 week. So I see. All right. Let me talk of calculating the number of modes. Number of modes. We can calculate the number of modes in an optical fiber using the V number. N is equals to V squared over 2 for step index optical fiber. Step index optical fiber. Then we have N is equals to V squared over 4 for graded index optical fiber. What is this? The number of modes. We say due to the interactions of the electromagnetic and electrical and the magnetic fields of light is a wave. it leads to adenoma modes. It means my optical fibers here to now I have adenoma modes. Single mode, multiple modes. Right. If you have a step index optical fiber, if you have a step index optical fiber, let us start by, right, what is a step index optical fiber? A step index optical fiber. Someone to give me a definition before we before I explain the number of modes in a given optical fiber. Let us define those two: step index optical fiber, graded index optical fiber. Anyone to respond? What are those two? Nada. Okay. Step index optical fiber is the type of optical fiber where you have a uniform refractive index for the core. Uniform refractive index of the core. This is the refractive index of the core. The optical fiber is like this, 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 this. This is the core N1, this is the core N2. The refractive index between this point and this point is the same, uniform. Same, let me say same, not uniform. Same and for the core. For the core. And here at this point, it is the same, the refractive index. It is the same. It can be represented by a profile where we have something like this. Right. And this is the value of, let me put it like this. This is value of N2. This is the value of N1. At this point, N1 is the same. If it is 1.45, it is the same 1.45. At this point, 1.45. At this point, 1.45, 1.45. It is the same at any point in optical fiber. That is what we call a step index optical fiber. And for the gradient index, the difference is in the difference in the refractive index. Now we no longer have the same. So this is my core, this is my cladding, N2, N2, this is my core. The refractive index is no longer the same, and the profile will look like this. For N2, it is the same, but for N1, it is something like this. It's no longer the same. So this is N2, and from here to here, we have N1 range of the values of N1. Right. What do I mean by that? It means at this point here, the refractive index is equal to around this value here. At this point, the refractive index is this value here, which is not the same. These two are not the same. At this point here, we have another value of the refractive index. The refractive index increases as you go towards the axis, towards the center, and increases as you approach the axis. That is what an graded index optical fiber is. We will later discuss why we have this type of optical fiber graded index. It helps in minimizing what we call dispersion. Pulse broadening, layman terms. We will later on discuss that. But for now, this is the definition. You need to know what a step index optical fiber is. You need to know what a graded index optical fiber is. How you let me know that you know is by drawing this. Explanations, paragraphs, they don't mean much to me, but I understand this language here. This is your profile of the optical fiber. For a step index optical fiber, it is a step. That's why it's called the step index. This is the step right there. Step index optical fiber. For graded index optical fiber, it no longer is a step, but something like a curve like this. And that curve means the refractive index in the core, it is not the same. It is not uniform, if I can say. All right, definition, step index optical fiber, graded index optical fiber. Now, if you are given a step index optical fiber, calculate the number of modes that can be propagated in that optical fiber. You use this formula, where V is the V number. So from our calculations here, we can also have, we said we are given N1, N2, find the numerical aperture, A, lambda, find the V number. From here, we're going to also have calculate the number of modes. Calculate number of modes. So you use that V you got here to calculate the number of modes. At the same time, the question can begin with, what are step index optical fiber? What are graded index optical fiber? You are given a diagram. An optical fiber looked like this. Where are we? It looked like this. What is the number of modes which will propagate an optical fiber? Now it's up to you to identify if you have something like this. It means this is a step index optical fiber. How do I calculate the number of modes in a step index optical fiber? V squared over 2. Simple mathematics. And that is it for the V number, a number of modes, step index, graded index. And we move on to losses. Any questions? Any questions so far? My videos are, you should be asking questions. If you don't ask questions, I will have to assume that everyone knows, which is not the case. But I'll make that assumption. Ask questions. Nope. Nope. Yes. Right. We go on to my losses in my optical fibers. Losses in optical fibers. There are bound to be losses. That is how you lose power in the light you're transmitting. You lose power, quality of transmission decreases. How does that happen? How does those losses happen in optical fibers? Although they are at a minimal, because of obviously the structure of the optical fiber, less EMIs, electromagnetic interferences, it means less loss, but there are losses. How does these losses happen? Makaverenga, any type of losses you know. Makaverenga. I think this is video number 5.
Radiation loss.
Radiation, radiative loss. Yes.
Chromatic dispersion loss.
Chromatic dispersion. Yes, we have dispersion. That is loss.
Bending losses.
Bending losses. Yes. Yeah. I never mentioned
alignment losses.
Alignment loss. Who is that?
This is memo.
Tagadi, alignment losses. Yeah, that is well. Well, I wasn't expecting that answer. It means you know what you're doing to an extent. Right. Losses in optical fibers. Right. We have our wave. We said we have pulses. This is how the transmission happens. This is a 1, 0, 1. We talked of digitalization. We are now sending 1, 0, 1s. Then anosangana light, and the light turns on, off. Layman terms. It is not ideally what is happening, but so that you get a picture at least. This is what is happening from optical fibers. We have those 101s. That is your information. We now know we can convert a voice message to this. We can do that. Now, when they interact with the light, then they are transmitted. This is the transmission side. And here we have our optical fiber. This is the receiver side. What will we receive on the other side? Most of the times, you will not receive exactly the same thing here. You might have losses. And this diagram will perfectly explain how those losses, what are those losses and how those losses happen. Point number one, how do you know we have a loss there? We have a change in amplitude. The amplitude decreases. You need to know my waves. I don't need to over explain what is the amplitude. This is the amplitude. It decreases. Maybe diagram around is a bit off. Let's have something like this. Let's have something like this. This is the same information being sent at the TX, at the RX here, at the receiver. But what has happened in between? There are losses. Change in amplitude. Amplitude decreases. Loss. If amplitude increases, what is that? What do you call that? If we have something like this as output, what has happened in between? What do you call that? But one with telecommunications, there's a word for that. What happened there? Amplification. Amplification. That is amplification. Now this is loss. This is amplification. Right. We also have change in the width. The width of the pulse changes. This is the width of the pulse here. Here, very, very small. There it is much, much bigger. The width of the pulse changes. We have those two types of changes which we can define loss from a pulse is edu in optical fibers. Right. Change in width. It can be related to change in duration. Duration of the pulse. What do I do here? Right. Duration of the pulse. Duration of the pulse. If I have a pulse like this is duration of the pulse here. The duration of the pulse should be kept at a minimum. The duration of the pulse should be kept at a minimum. Why? Because it is related to the bandwidth. And bandwidth here do something like this. This is the duration of the pulse. Let's just say T. For now, let's give it a T, not delta T. Duration of the pulse, T. It is inversely related to the bandwidth of a given channel. So if T is at a minimum, it means we have high bandwidth. And obviously for telecommunications, we need high bandwidth. So we need to keep T at a minimum. T should be kept at a minimum. But what happens when you have losses? The width changes, it increases. If the width increases, T increases, then we have minimum bandwidth with minimum, not minimum bandwidth, less bandwidth. With the less bandwidth, it means the quality of our communication system decreases. Quality of communication system decreases, that is loss. That is what we call a loss in a system. Right. Amplitude. How does the amplitude affect, or how do we define loss in terms of the amplitude of that pulse? I defined the width with the time, the duration of the pulse. If it increases, the bandwidth decreases, that's a loss. Now for the amplitude, detection, right? Per block system redu, you have transmission side, we have our channel, we have our receiving side here. Receiving side here, in between panel, Tinina's optical detector. Optical detector. So what the optical detector does, we have signal redo 101. It is sort of a threshold, the optical detector here on the receiving side. It is sort of a threshold. Let me say this is the threshold. Right. What does the threshold do? If a pulse is like this, threshold, it is detected as a 1. Can I repass threshold? It is detected as a 0. So you can go up and up, 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 up. This is a 0. This is a 1. This is a 0. This is a 1. This is a 0. This is a 1. Above threshold, below threshold. That is how detection basically works. Now you can see that detection determination yacho, yeah, on the other side of the receiving side, it is determined by the amplitude of the pulse. So pakaitika any changes in the amplitude, for example, in our case, the amplitude decreased. Amplitude here because of the loss, you so let me do this. Let me do this here. Amplitude. What is a loss? Pop up. Amplitude area 1. Now, what is happening here? Instead of detecting 101 at the other end, you end up detecting a 111. Well, something happened to the amplitude. 1 at this point, this is another 1 at this point, this is another 1. Instead of getting a 0. This is loss. If you cannot detect information that you transmitted correctly, that is loss. So these are the two forms of malosses that no cancer with a change in width and the change in amplitude. It can happen as well. Signal amplitude to decrease totally like this. Now this is a 0, 0, 0 because of our threshold here. Threshold. We are below the threshold, that is 0, 0. But what did I transmit? I transmitted a 101 loss of information. So if you are to explain, describe what loss is using an optical pulse, you explain it in terms of the width and the amplitude. Here, affect the detection. Here, affect the bandwidth, duration of the pulse. Right. A simple way. How can we? Let me find an English word. How can we make a signal go from this in the transmission side to this in the receiving side? What happens in between here so that we keep the integrity of the pulse? Or let me say, how do we minimize my losses for the width change and the amplitude change? Question. More videos. What do you think?
I think we used my repeaters.
Yeah, we are not very good. That was the first response I was looking for. What is a repeater? Making use of my repeaters. What is a repeater? What is a repeater? Pananza repeater here. What is a repeater? Yeah.
It is a device that is used to replicate the device of the. In fact, it's the device that is used to replicate the same the original shape of the signal.
All right, it replicates the original. Original. Okay, let's say original shape of the signal. So how does the repeater works? We have that signal here. Over the length of the optical fiber ready zero. Instead of having optical fiber iso transmission side, receiving side, you know a signal like this. What do? One way of making my changes on is a repeater at this point. What the repeater does at an interval, you put repeaters at intervals. For example, this is a maybe 10 kilometer optical fiber. Here, 10 kilometers there. You put my repeaters in between at intervals. What the repeater does, it replicates this signal. Reaches up, it is replicated, so that at least you keep the integrity of the original pulse. Why not amplification? Why are we not using an amplifier? We can use an amplifier here. So that signal in the amplifier, it is amplified. It is amplified. Why no one mentioned amplification? Why do we not amplify that signal? You need to know that. And I think my videos, I think so. Why not amplification there? Question. My question is, am I right? Why not? What is amplification? No. Amplification, amplifier. Amplifier need to say.
An amplifier boosts the signal.
Yeah, let's use
It
boost.
is actually used.
It's actually used. Okay. It's more than me. Dog amplifier. All right. Amplification is, let's say, boost. If you have a signal like this, because amplifier, that is amplification. In simple terms. Why are we not amplifying that signal to do something much better on this end? Chief, why are we not amplifying? Or we want to define amplification? All right,
I wanted to define amplifier.
Define amplifier, Chief.
It's like we are integrating the signal.
Integrating with what?
We're integrating the signal. You know what, Martin?
Okay, integrating the signal. I wanted with what? What are you integrating with? I have 1 minute left here. All right, amplification. Increasing the amplitude, boosting, increasing the amplitude. Here we increase the amplitude. That is amplification. Why don't we use amplification here? Question number 1, assignment number 2. Why don't we use amplification there? That is question number 1, assignment 2. I end this session here. Join me soon after because the matters no dura.